Okay, this is about the circuit. This is, I think you check the advanced, no? You see the number of times they've asked it. Plenty of times. Rotation mechanics important, potentiometer important. I say potentiometer. Ammeter, voltmeter, grouping of cells, series, parallel, V-stone network. You see, these are the very favorite topics. Rotation mechanics, potentiometer. I say potentiometer. Meter bridge, rotation mechanics, meter bridge. These are the things which you have to really focus. Exam point of view, I'm telling. Rotation mechanics is very good chapter. Okay, good. But exam point of view, potentiometer very important than rotation mechanics. Now, this is cell whose EMF I don't know internal resistance, and EMF somehow I calculated by previous method. So this is the galvanometer. This is a jockey. So let me keep it at A. This is B. I think this was C2, no? Earlier we took it. So this is a galvanometer. So current through galvanometer is 0. I is 0. I'm just going to continue the same discussion what we made earlier. So what was the balancing length? L2. So this was the terminals A2 and B2. Current through galvanometer 0, no current flows here. I will provide another circuit. This is the external thing, and let this be a switch. Okay, now with switch S open. First condition is what? Switch S open. Then a current through galvanometer, the balancing length is such that no current flows through galvanometer, and that current I will pass through the circuit like this. No current will flow here. I think I'll make it in this way. So no, okay, yeah, let it be here. So this is IG, no? IG 0. No current flows through it. And anyway, there is an open circuit, no current will flow this resistor. What is this R? External resistor. External resistor, whose value I know it. Known, I know that value. So tell me, like, what is the this VA again? Current to galvanometer is 0. So therefore, VA equal to VA2, VC2 is equal to VB2. So therefore, VAC2 is equal to VA2 B2. This already we know. What is VA2 B2 is what is VAC2? This should be equal to I lambda 2. What is VA2 B2? So we'll write loop equation. Whenever you are in big trouble, take help of loop equation. V2 minus EU minus IG into RU minus VB2 0. So as IG 0, so therefore VA2 B2 is equal to EU. When you're in big trouble, just take help of the KVL. So what is the value of VA2 B2? I should write equal to EU. Keep it in whose EMF I know it. Now what I do is like I'll close the switch. Let switch be closed. I'll write all the values here. So it'll be same thing. Let me continue here. There's a known thing. Okay, so this much is what we have with switch S open. We have this much of information. I'll take it all this. Okay, now let me close the switch with switch S closed. Now let me close the switch. There's a potentiometer, same circuit, only I'm going to close the switch. This is A, B. This is cell. It will decrease a little bit now. Let me call C3. I'll move a little bit because the terminal voltage should be less than applied EMF, no? Because they may ask you any logical questions like this also. This is L2. Okay, this is L3. Now you have to be a little bit careful here. A3. The same thing, actually the terminals I'll give some different symbols. This unknown EMF, which we already know. This internal resistance we have to find out. I'm going to close the switch. The switch is being closed. Any changes will come here. Now I'm going to slide the jockey in such a way that current through galvanometer again will become zero. No current flows here, but there will be a flow of current. There will be current, I'll call I dash. I dash will flow here. Capital I will flow here. Capital I will flow here. The current in primary circuit. This is called like a primary circuit. This is called like a secondary circuit, or they call primary cell, secondary cell. This whole circuit you can give him primary circuit. This is everything you can call it as secondary circuit. Okay, now see that no current will flow through here. Why no current flow? The jockey position is so adjusted that VAC3 is equal to VA3B3. And the current through the galvanometer will be zero. So then immediately what are the conditions? I'll write it. VA is equal to VA3. Then similarly VC3 equal to VB3. So with this, what we can write? VA C3 equal to V equal to VA3 B3. And what is VAC3 equal to? Should be equal to I lambda L. See, I think this will be really troublesome for how come, sir, like here you say current will flow here. Here no current flows as these two, this capital A and A3 are at same potential. C3 and B3 are at same potential. That's why no current to galvanometer. How do I come to know? I look at the pointer. The pointer in the galvanometer will show zero deflection. So this shows that no current flows to this path. No current flows. Sir, current will not flow here. Current may flow here. I think again go for conservation of charge. What current that leaves here, that much of current should follow here. And what current leaves positive terminal here, that much of current should pass here. If any current flows here, law of conservation of charge will be violated. If you want to connect one more galvanometer here and check it, that's all. No. If you're really very big troubles are not getting, you connect galvanometer here, it will not show any deflection. But you connect any galvanometer here, there'll be deflection, there'll be deflection, there'll be deflection, here deflection. And if I connect galvanometer, deflection, you can't connect here, huh? It's inside the cell. If you connect one more ammeter here, it will show deflection. So here no current, here no current. But that's what happens practically. If you want, you can connect ammeters and check it finally. Okay, we got now These are the conditions. So let's come look at the cell now. Look at the cell. Now current is flowing through the cell. So what will be the voltage? Is it VA3, B3 is equal to applied EMF? No, it will be less than applied EMF. So it's equal to terminal voltage. What we are measuring now? Terminal voltage. What earlier VA2, B2, the terminal voltage was equal to applied EMF, you see. This now what we measure is the terminal voltage only. So therefore now this what I'll write is like a I lambda L3. Don't go for writing anything, just leave it. Don't write value of this VA3 B3. What is equal to I lambda L3? I connected one external resistor. So any formula now, any formula relating all this. So we have directly one formula now. Internal resistance should be equal to applied EMF by terminal voltage minus 1 into R. So do we know value of EU? I lambda L2. Do we know value of terminal voltage when current through galvanometer is 0? I lambda L3. And the external resistance, we know it. So finally, what is R is equal to lambda 2, lambda 3 minus 1 by R. If you change capital R, L3 will change. L2 is a fixed value. L2 is obtained from some other condition. You check it here. From other circuit, what we obtained. So like this, I'll measure the internal. If you vary capital R, small r will not change. This is a fixed value. If you vary capital R, L3 will change. So as you vary the resistance, the balance length, this will change. Okay, got this. So when you are measuring internal resistance, what you should do, you have to see that a current must flow through the cell. Then you measure terminal voltage. That terminal voltage is proportional to balancing length. So in the experiment, what happened, what you should do, first you should take a cell whose EMF is known, calculate the balancing length. Then calculate the unknown EMF for balancing length L2. Then bring one resistor R, connect parallel to the cell, close the switch. Then again, you adjust the position of jockey so that current through galvanometer is 0. Measure the balancing length L3. Substitute here, and you know what resistor you are connected. You'll get the internal resistance. See, anything if it is very complicated for you, you should take help of KVL, writing KVL, writing KCL. So like this, this is the internal resistance of a cell. Okay, there's a theoretical background. So everything is all about now the situation. Based on these two situations only, all the numericals will revolve. And let's come for the basic thing. What is this standard cell? What is the key? See, like I want to do some adjustment. I should see that the current through the potentiometer wire should be 0 when I'm doing some adjustment, because galvanometer is a very sensitive element. So therefore, I'll first open the key. I'll just open it. Open means I'll remove the plug. On off switch similar to that. Then what all any adjustments are there, I'll do it here. Then I'll switch on the key. So the key is very important here. The key is very important. So usually like an on off switch similar to that. With a standard cell. So you must know value of E naught R naught may not be required. You can see nowhere the necessity of E naught R naught is needed here. So if it is a current through galvanometer not 0, then what to do? It will become like a two loop problem. Then you have to work out applying KVL loop currents I1, I2, or branch current or nodal analysis, whatever you want. Then you have to call. So what is the type of problems? Three types of problems: finding out unknown EMF, finding out internal resistance when current through galvanometer is not 0, or when bridge is not balanced, potentiometer is not balanced. Balance means current through galvanometer 0 will call balance. Unbalanced means current through galvanometer is non-zero. When it is balanced, simple formula. When it is not balanced, current through galvanometer non-zero, then it's a two-loop problem. Okay, fine. So anybody, any doubt? If you want, you can ask it. I'll start the numericals. I will start the numerical. Okay, fine. Just only if you are very get confused, no, use different symbols like how I brought no A2, B2, then potential set A3. So these are very important observations.